Morning, pre-calculus class today. We'd like to talk about chapter 8, the continuation, and 8.3, trigonometric form for complex number. So the way to convert that complex number to the trigonometric form, and there's certain kind of formula that I need to emphasize here. But before we get started, so let's get some kind of a review for the complex number. So something that you learned from Algebra 2. So we'll take a look at that. Okay, so complex number and polar coordinates. So we do know that I is considered a square root of -1, so I squared would be -1. So I is the imaginary unit number in the form a plus bi are called complex numbers. So a is always considered the real part, the real number part of the complex number, and b is the imaginary part. So if a is greater than 0, then square root of -a, so that equals I root a. So for that square root of -1, so we just consider that it's I. So it's just the imaginary number. So here are some of the examples. So I don't think I need to re-emphasize that because something that you guys should already know. So things that you learned from Algebra 2. So square root of -25. So separate that square root of -1. I root 25. Perfect square number. So it's written as 5i. And then the rest of this. So simplifying. And also, anytime that you multiply by the complex number, make sure that you need to convert that to the I form first before you multiply. So something like d right here. So I root 3 times I root 3, then that'll be I squared times root 3 quantity squared. So it's -1 times 3, -3. And then quotients. So anytime that you deal with the quotient, again, complex number, we write it as the imaginary number part. So separate the I first. And then anything that can be reduced, so try to reduce it. So 98 over 49, so then that'd be 2. It's under a radical, so it's I root 2. So now let's take a look at that, something else, solving. So solve x equals -25. So x squared equals -25, so square root both sides. We do know that's a quadratic. It's a quadratic equations. But the thing is that you're dealing with the square root of negative numbers, so that's why we need to separate the I. So separate it out. So we do have plus minus I root 25. So x equals plus minus 5i. So here's another example, quite similar to the previous one. So separate that I, and then also 54 is a non-perfect square number. So that's why we need to break it apart into a perfect square number and a non-perfect square number. So eventually we end up with plus minus 3i root 6. So multiplying, again, separate out the I, quotients, again, separation with the I, and then reduce if that's possible. So addition, subtraction of complex numbers. So this one is quite straightforward. So basically this one, I just want to group the like terms, so the real number. So that's all together. So that A and C, those are the real number part. And then B and D, the imaginary number. So just group them together. And then A minus C, similar. And then B plus D. B minus D, because that's the subtractions. So you want to group those together. So for example, we do have 4 minus 6i plus the quantity of -3 minus plus 7i. So you want to group the real numbers together and then the imaginary numbers. And then you want to just manipulate them, additions, and then the other one is just subtraction. So similar to the previous one. So 10 minus 4i minus the quantity of 5 minus 2i. So the real number, group them together, imaginary number, group them together, and then, so you just want to follow through the operation with subtraction. Okay, so now let's see what else that we have. Complex number, multiplication. So this one, basically, it's about FOIL. So for that, A plus BI times C plus DI. So the way to rewrite it eventually, so it's going to be A times C minus B times D plus the quantity of AD plus BC, and then times I. So once you FOIL first, outside, inside, and last, you want to group the real number and then the imaginary number. So the product of two complex numbers is found by multiplying as if the number were binomial and using the fact that I squared equals -1. Okay, so things like this. FOIL first, outside, inside, last, and then you want to combine the like terms. So one thing, keep that in mind, I squared is always -1, so 6 minus 20, -1. Then that'd be 6 plus 20, so which is 26. So minus 2i. So this one is quite similar. You can expand it by using the binomial expansion theorem. So 7 squared times 2 times 7 times 3i plus 3i quantity square. So 7 squared, that's 49. 2 times 7 times 3i, 42i. And then 3i quantity square, so it's 9i squared. Again, I squared is -1, so combine the like terms. So 49 minus 9, then that'd be 40 plus 42i. So here's the I power. So the I cycle, we talk about that in algebra 2. So I to the first power is I squared is -1, I to the power of 3, -1, I to the power of 4, which is 1, I to the power of 5, 1. And then the rest of this is going to be the repetition. So I to the power of 6 is the same as I squared, back to -1. I to the power of 7 is the same as I to the power of 3, I to the power of 8. So this one can be written as I squared and then to the power of 4, power, so it's 1. I to the power of 9, back to the I to the power of 5. And then I to the power of 10 is the same as I to the power of 6 and I squared. And I to the power of 11, it's -I, same as I to the power of 7, I to the power of 3. And then I to the power of 12, 1. So basically you can use that the power exponent property, the exponential property, so you can expand it as like power of power. And then you can use the I cycle from the first power to the fifth power. So you can repeatedly doing that, the I cycle. So simplifying I to the power of 17, so this one thing we notice, I to the power of 4 is 1, so we just split it into I to the power of 16, which is written as I to the power of 4 times 4, and then times I to the first power. Again, I to the power of 4 is 1, so 1 to the power of 4, that's 1. I, nothing we can do with that, so it's 1 times I, which is I. And then this one is 1 over I to the power of 4, which is 1 over 1, so that's 1. Properties of complex conjugates. So anytime that you multiply by the conjugate, you'll end up with things like this: a squared plus bi, a squared plus b squared. Excuse me. So for example, so anytime that you need to rationalize the complex number, especially the denominator, so we multiply the conjugate of the denominator top and the bottom. So once you multiplied it, so the top part you want to distribute, FOIL, denominator. Excuse me. So for the denominator, so just use that the difference of two square patterns. So it's 4 minus I squared. So the top part, just combine the like terms. The bottom part, so it's 4 plus 1, which is 5. And also this one can be separated. So 7 over 5 plus 11 over 5i. So the product of a complex number and its conjugate, it's always a real number. So we modify the familiar coordinate system by calling the horizontal axis in the real axis and the vertical axis as the imaginary axis. If you try to plot the point for the complex number, and each complex number, a plus bi, determines a unique position vector with the initial point 0, 0 and the terminal point a, b. So for example, so let's say we do have a complex number plane. So the x-axis is still considered a real axis, and the y-axis is called the imaginary axis. And let's say that we do have a terminal, r, the radius. So let's say that we do have x plus yi. So that gives you the initial position from 0, 0, the origin. And then all the way to that point P right here. So as you can see that we do have an x-axis, the horizontal axis, which is the horizontal distance. And then the y distance here, so the vertical distance. So that comes out with the right triangle. And one thing that we notice, x equals r times cosine of theta, and we talked about this one previously for the previous sections, and y equals r sine theta. By using the Pythagorean theorem, so we find out that r equals square root of x squared plus y squared. Another thing that we notice, tangent of theta, it's y over x. It's the vertical axis over the horizontal axis, if x cannot be 0. So the trigonometric polar form of a complex number, so the expression can be written as r times the quantity of cosine of theta plus I sine theta. And you may notice that r cosine of theta is just considered the horizontal component. And then I, r sine theta, then that'll be the vertical component. And keep that in mind, the vertical component, it's always the imaginary part. So this one is called the trigonometric form, a polar form of a complex number, x plus yi, so you can call it either way, trigonometric form, or the polar form. And the expressions cosine of theta plus I sine theta is sometimes abbreviated cis theta. So cis, that means cosine of theta times r, and then plus I sine theta. So that's just abbreviation. So using the notation, so this one can be written as r cis theta. Okay, so now let's find out some examples. So express that 2 cosine of 120 degree, 2 times the quantity of cosine of 120 degrees plus I sine of 120 degree in the rectangular form. So the one that's given here is the trigonometric form or the polar form. So now you want to convert this one back to the regular complex number form. So first thing that you want to do, you want to find out what cosine of 120 is. On a unit circle, that according to the unit circle is negative 1/2. Sine of 120, it's root 3 over 2. So once you rewrite it, so this one can be written as 2 times the quantity of negative 1/2, comma, I root 3 over 2. And then distribute, you'll end up with negative 1 plus I root 3. And notice that the real part is the negative and the imaginary part is positive. So this is consistent with 120 degree being in quadrant 2. Quadrant 2, so in quadrant 2, we do know that the sign change is negative positive. According to the rule, all students take calculus. So quadrant 2. So it's negative and positive. So converting from rectangular form to trigonometric form, step 1, sketch the graph of the number x plus yi in the complex plane. Step 2, find the radius by using the equation, the Pythagorean equations. And then step 3, find theta by using the equation tangent of theta equals y over x. X cannot be 0. Choosing the quadrant indicated in step 1. So for example, find the trigonometric notation for negative 1 minus I. So first find the radius using the Pythagorean theorem. So we end up with root 2. And then sine theta. So we do know that sine theta is considered opposite over hypotenuse. So we do have negative 1 over root 2. Rationalize it. We got negative root 2 over 2. And then cosine of theta, it's negative 1 over root 2. Adjacent over hypotenuse. So it's negative root 2 over 2. And then theta, for this one, we're using the inverse of the trig ratios, tangent. So we find out that is 5 pi over 4 because this one is allocated in quadrant 4. And thus, so this one can be written as root 2 times cosine of 5 pi over 4. And then plus I sine of 5 pi over 4. Or we can write it in terms of the abbreviation, root 2 cis, and then 5 pi over 4. So product theorem, so that's something you guys need to recognize. It's a new formula. So instead of just multiplying the complex number, which you can just convert that to the trigonometric form or the polar form. And for the radius, so we do have R1 and radius 2, R2. So for the radii, so we can just multiply those two radii. And then for the angle, we can use the angle sum theorem. We can use the sum theorem of cosine and sine. So cosine of theta 1 plus theta 2. And then for the imaginary part, so it's I times sine of theta 1 plus theta 2. So in the compact form, this one is written as R1 cis theta 1, R2 cis theta 2. So it can be written as R1, R2 cis of theta 1 plus theta 2. Again, this one is the abbreviations of the resulting form of the complex number in the trigonometric form. So find the product of 4 times the quantity of cosine of 50 plus I sine of 50 and 2 times cosine of 10 plus I sine of 10. So since we do know that radius 1 is 4, radius 2 is 2, so multiply those two radii, so we got 8. And then theta 1, we do have 50, theta 2, we do have 10. Combine those two angles, because that's product, it's a product, so it's corresponding to addition. So 50 plus 10, so we do have cosine of 60. And then for I sine of 60, similar, And then one thing that we need to find out, because we need to convert this one back to the complex number. So cosine of 60, we do know that it's 1/2. And then sine of 60 is root 3 over 2. So it's 8 times the quantity of 1/2 plus I root 3 over 2. And then distribute, so we do have 4 plus 4I root 3. And what about for the quotient? So quotient is quite similar. So product is corresponding to addition. And then quotient, guess what? It's corresponding to subtraction. Again, for those two different radius, so we just want to divide it. It's a ratio, so 2 radii. And then for the angle, since that's a quotient, so we're using that the difference identity of cosine and sine. So cosine of quantity of theta 1 minus theta 2. And then plus I sine of theta 1 minus theta 2. And also this one can be abbreviated into R1 over R2 times cis of theta 1 minus theta 2. So find the quotient. So we do have 16 times the quantity of cosine of 70 plus I sine of 70, and then 4 times the quantity of cosine of 40 plus I sine of 40. So first thing that you want to find out, determine the radii. So we do have 16 and 4. So 16 over 4. So we do have 4. And then it's a subtraction. It's a quotient, so that means corresponding to subtraction with the angle. So we do have theta 1, 70, and then theta 2, 40. So 70 minus 40, then we got 30. And then for the imaginary part, similar, so I sine 30. So we do have cosine of 30, which is root 3 over 2, sine of 30, 1/2, and then distribute with the radius, the quotient, the ratio of the radii. So we do have 4 times the quantity of root 3 over 2, plus 1/2 I. So we do have 2 root 3 plus 2I. The Morris theorem. So here's one of the powerful theorem for doing the polar form with the radius. So let's say that we need to raise up the polar form to a certain power. So instead of converting it back to the regular complex number form, so we just want to deal that with the Demovires theorem. So anytime that you deal with something like r times the quantity of cosine of theta 1 plus I sine of theta 1, and then the whole thing to the power of n, like a high order power, you can always distribute the power to the radius. And then for that angle, you can make it as like a multiple angle. So it can be written as cosine of n theta plus I sine of n theta. So in the compact form, so this one can be written as r to the power of n times cis of n theta. So now here's one of the examples. So let's say that you need to convert this one, negative 1 minus I, the regular complex number, to the 5th power. So find the trigonometric form first. So negative 1 minus I, you need to convert that to the polar form. So once you try to find the radius, so this one using the Pythagorean theorem, we do have root 2. And then find the ratios, find the inverse of the trig ratio, so you get the angle, which is in quadrant 3, excuse me. So it's negative negative, so 225, because that inverse of tangent of negative 1 over negative 1, it's the reference angle is 45 degrees, but it's allocated in quadrant 3. So it's 225. So once you convert that to the trigonometric form, we can use that the Morris theorem. So radius, so root 2, quantity to the power of 5, so we do have 4 root 2. And then the rest of this, we just need to insert that power with the angle, multiply 5 and 225 together, so we do have 1,125. So cosine of 1,125. So this one will get back to quadrant 1, so we do have cosine of 1,125, which is root 2 over 2. And then sine of 1,125, which is root 2 over 2. And for those you might be wondering, well, why is positive positive? Because that once you find the coterminal angle, so that means the angle is getting back to quadrant 1, okay, the first quadrant. So distribute eventually, so we do have 4 root 2 times the quantity of root 2 over 2 plus I root 2 over 2. So we do have 4 plus 4i. What about the nth root? So let's say that we need to take the nth root of the complex number. For the positive integer n, the complex number a plus bi is the nth root of the complex number x plus yi if the quantity of a plus bi to the power of n equals x plus yi. So here's the situation. So let's say that we need to find out nth root of r times the quantity of cosine of alpha plus I sine of alpha. Okay, so something like this. So we need to find out what alpha is. So first thing that we need to determine the angle theta. And this one is just the repetition, because we can go around the unit circle as many times as we want. So plus 360k divided by n. So n, it just tells you that the index number for the root. Or this one can be written as alpha equals theta over n plus 360k divided by n. So k, you can try it like multiple times. So k equals 0, k equals 1, k equals 2, until k equals n minus 1. The reason why is k equals n minus 1 because we need to find out the closed root to the complex number with the polar form. So find the square root of 1 plus root 3. This one's supposed to be 1 plus I root 3. So convert that to the trigonometric form. We do have 2 plus 2 times. There's supposed to be I here, so behind, so it's hard to see that. It's after the closed parentheses. So it's 2 times the quantity of cosine of 60 plus I sine of 60. If you try to convert it back to the polar form. So this one is written as 2 times cosine of 60 plus I sine of 60, the whole quantity, to the power of 1/2, because that's the square root. So using that, the pattern, we do notice that is 2 to the power of root 2, 1/2, excuse me, so it's root 2. And then the rest of this, so using that, the structure, so we do have theta over n plus k 360 over n. Okay, so for the imaginary part, similar, but with the I. So reduce it, so we do have cosine of 30 plus k times 180, and then plus I sine of 30 plus k times 180. So, and then you want to do the multiple tests. So k equals 0, k equals 1, because this one is 1/2, so that means we need to get all the way down to k equals 1. Again, we need to find out the root, which is getting close to 1/2 for the index number. So what we got here is root 2 times cosine of 30 plus I sine of 30, because k equals 0. And then when k equals 1, so it's root 2 times the quantity of cosine of 210 plus I sine of 210. Again, just plugging k equals 1 here for the second part. Okay, k equals 0 plus just plugging k equals 0, and then you come up with this. So find all for root of negative 8 plus 8i root 3. Write the root in the rectangular form. So first thing that I want to do, convert that to the trigonometric form, like what we did previously. You'll get that it's in quadrant, well, it's negative positive, so it's quadrant 2, so that's why the angle is 120. So using the Pythagorean theorem, find the radius, using inverse tangent to find out the inverse tangent ratio with the angles 120. So radius is 16, and then theta is 120. So this one, take 4 root of 16, so we do have 2. And then alpha, this one can be written as 120 over 4, because the index number is 4th root. And then plus 360k over 4. So just try to simplify it first. And then we put into the regular form. So k equals 0, so alpha would be 30. K equals 1, then alpha would be 120. K equals 2, then alpha would be 210. K equals 3, then alpha would be 300. So once you rewrite it, so we do have 2 cis of 30, and then 2 cis of 120, and then 2 cis of 210, and then 2 cis of 300. Again, that's the root with the radius, so then that'll be 2. Because that's back to the previous slide here, showing this one is 4 root 16. So 4 root written in rectangular form, so we do have root 3 plus I, negative 1 plus I root 3. You try to evaluate that, each one of those, back to the complex number form. Negative root 3 minus I, 1 minus I root 3. So it's quadrant 1, quadrant 2, quadrant 3, quadrant 4. And the graph of the root are all on a circle that has the center at the origin, and the radius 2. So which means that once you find the zeros for the complex number, so that's going to be all those 4 solutions there with the complex number plane. Polar coordinate system. The polar coordinate system is based on a point called the pole, and the rate called the polar axis. We talked about this one previously for the graph. So, and this one is just a quick refresh. And the main important formula that I need to know in order to convert that from rectangular form to polar form. So x equals r cosine theta, y equals r sine theta. Radius, so Pythagorean theorem, tangent of theta is just the inverse of opposite over adjacent with the y-axis over the x-axis. Okay, so anytime that I need to convert something like this, the polar form back to the rectangular form, so using those formulas, so we do have x equals 2 cosine theta, so which is 2 times root 3 over 2, root 3, and then y equals 2 sine theta, so 2 sine 30, so 2 times 1/2, which is 1. So the rectangular coordinate, it's root 3, comma 1/2. Convert 4, comma 2 to the polar coordinate using the Pythagorean radius formula. So we got the radius 2 root 5, tangent of theta, find the angle, so inverse of tangent of 1/2, which is 26.6 degree. You can always convert that to radian, multiply that angle by pi over 180. So rectangular and polar equation. To convert rectangular equation into polar equations, so we need to use that identity. X equals r cosine theta, y equals r sine theta. For the linear equation, it's ax plus by equals c. We can just use that the substitution form. So r equals c over a times cosine of theta plus b sine theta. Or that one, you can just like cross multiplying it. So let's say that you need to convert that x plus 2y equals 10 into the polar equation. So again, using the structure, so r equals c over the quantity of a cosine theta plus b sine theta. So we do find out that c is 10, and then a, which is 1, b is 2, is a linear equation. So it's 1 cosine theta plus 2 sine theta down the bottom, and then the top part is just 10. Graphing, so you can always, using that theta r table, plug in the special radian, and then find out the radius. So we do have, this one is a circle. We talked about that for the previous sections. And then the paddle. So the structure, r cosine of n theta. So it's a flower paddle. So this one is a n equals 3. It's an odd number, so it's 3 paddle. And converting r equals negative 3 cosine theta minus sine theta into the rectangular equation. So again, this one, what we can do, we can just multiply by r both sides. So once you multiply r on both sides, we can use the Pythagorean identity here. So r squared equals x squared plus y squared. And then r cosine theta can be replaced by x. And then r sine theta can be replaced by y. So this one turns out to be x squared plus y squared equals negative 3x minus y. So it's kind of like a conic section. For those who might be wondering, it is. So once you convert it, so it's x squared equals negative 3x minus y squared. Or you can just leave it as this form right here. So circle and Lemniscates, so those are something that we talked about already. So r equals a cosine theta is always like a circle on the first and the fourth quadrant. So r a sine theta, so in the first and the second quadrant, is also a circle. And then r squared equals a squared times sine of 2 theta, double angle with the quadratic. So this one is a symmetrical loop. And then r squared equals a squared cosine of 2 theta. So this one is also the symmetrical loop, but it's considered reflected over the x-axis. And this one is reflected over the line of symmetry of y equals x. Okay, so, and the rest of this, the lemnicon, so something that we talked about already. So a over b is less than 1. If you see the structure, r equals a plus b plus minus b sine theta. Or r equals a plus minus b cosine theta. So you see the lemnicon. Okay, so like a loop, outer loop, inner loop. And then the one without the inner loop here. So a over b is equals 1. So anytime they see the ratio a over b is less than 1, so there's always like in the loop. If you don't see anything like that, it's always like a little bump here. Okay, so right between 1 and 2 for the ratio. So we do have this sideway, the small bump. Okay, and then over here, a over b is greater than or equal to 2. So we do have like a giant big loop, so going around all 4 quadrants. Okay, so now thank you for watching the video today. So any question, any comments, so please put up on the YouTube channel. So I'll see you guys next time. Thank you for watching it.